In this lesson, we will take a look at the chain rule, which is used to find the derivative of composition functions. First of all, we'll just take a look at the notation. Now, I'll honestly say this whole sentence at the top, I won't read that, insult you and read that for you, but this is the type of thing that made me really uncomfortable when I first started studying calculus because it's so wild, but it's really necessary. And when we really fully understand what's happening, then we can go back and apply some of this notation. Even so, as I'm speaking notation, here is the chain rule in just notation form. This means that this format works for every differentiation example or exercise when the chain rule needs to be applied. So we won't let the notation scare us. Let's just go up forward and talk about what happens. Take a look at how we actually utilize this whole scary looking notation, and then if you're interested, you can certainly go back and read through some of this definition and notation that represent the chain rule. An important concept is to know when you should use the chain rule. So let's do a comparison here. I love comparisons. It always helps me understand. So using this function, if this were a function to the left, x raised to the fourth power, I would just use maybe the product rule or just other rules. I'm putting this in the other rules category. But the chain rule is used when that x is a quantity. And so here's an example. We have quantity of 3x plus 8. And so instead of just an x being raised to the fourth power, that quantity is being raised to the fourth power. So that's what we mean by a composite. So we'll use the chain rule in this example. Here's another example, the sine of x. Fundamental, or actually a common function in which we would differentiate or find the derivative of it. And so we have the sine of x, but we have to use the chain rule when we have for example, the sine squared x or the sine x quantity squared. And so we see sine squared x very often, but know that sine squared x can also be written as sine x quantity squared. And so we're looking at the need for the chain rule because we have a composite. Here's another example. Notice how on the left we have the cosecant of x times the cotangent of x. So we're talking product rule. But on the right, we have the cosecant of the cotangent of x. So instead of that x being there with the cosecant, we're talking about the cotangent of x instead. Again, a composite. And here's another example. E raised to the x power. Very popular, very common. We use this, we find the derivative of this one very often. But then if something is being done to that x that's in the superscript, for example, the sine of x, or if we had 2x or the square root of x or anything up there with that power, then we're looking at a composite and not just a standard function. And so that will be time to use the chain rule to our advantage. So let's take a look at this example. We have y is equal to a quantity of 3x plus 8 raised to the fourth power. And so we should recognize this as time to use the chain rule because we don't have just plain old x raised to the fourth power. We have a quantity. So this is an example of a composite of functions or a composite function where we need to deal with every aspect of this multifaceted situation. And so the first thing I'm thinking is y prime is equal to the product of two things because that's by definition how the chain rule works. Two things get multiplied, and I'm just going to go with y prime just to cut down on some of the notation. But then we should be thinking about, okay, what two things are getting multiplied? First, I'm going to deal with the derivative of this entire piece, as if it were x to the fourth power. So I'm going to go with that power rule and just pull down that 4 and lose a power. So we've practiced this quite a bit. At this point, we should have 4 times the quantity of 3x plus 8 raised to the 4 minus 1. Of course, that will give us the 3. And then the next thing we should be thinking about is the product of, the derivative of this inner piece. And so that's what we multiplied next. We have 3x plus 8, and so the derivative of that, of course, we've practiced at this point, is just 3. And so now we continue with simplifying because we've employ the chain rule, and the rest is just algebra. And so I'm going to look at this thing really, as I draw it down, it really is 4 times the quantity 3x plus 8 raised to the third power times 3. So that's just 3 things being multiplied by each other, which of course we can multiply in any order we please. That 3 and that 4 can certainly go ahead and multiply, which leaves us with with a 12 in as that coefficient. And so now we just have 12 times the quantity of 3x plus 8 raised to the third power. Now remember, the idea here is, what is the slope of some particular tangent line to this curve? And so the result is, or we would respond in this way. This is the slope. So if you want to double check your work, be sure to whip out those calculators, graph your original equation, and then graph your resulting equation and make sure it looks like a slope of that a line whose tangent with a tangent on this curve that actually meets your original curve. In this example, we're given a quantity, -5 minus the quotient of 8x over 5, and that's all being raised to the -5. So it looks kind of messy, but we do recognize it as a composite in that we do need to use the chain rule, because remember, it could have just been x raised to the -5, but then we've got all that other stuff happening inside of that parentheses. So we'll employ the chain rule. And so when we're finding, because of that, we'll be thinking about 2 different elements needing to multiply. First, the derivative of this entire thing as if it were x raised to the -5. So we're just going to use the power rule, pull that -5 down, and leave what's inside there, and then we subtract one of those powers. And so now we have -5 times that entire quantity, all raised to the -6. And so that's just one piece of this. And then the other piece is to deal with what's inside of that parentheses and find the derivative of that one. And so immediately upon looking at this, we're thinking about a couple of different rules that we can use. The sum and difference rule. And so we definitely, because we have the difference of these terms, -5 and 8x over 5, then we're thinking, okay, I definitely have to differentiate them both. But then when we're dealing with the 8x over 5, that would be the quotient rule. So we need to employ those as they fit. So definitely, because of that quotient rule, we're going to have to deal with the 8 over x. Fortunately, the -5, when I differentiate that, it goes out to 0. So we're just left with dealing with that -8x over 5. And so the quotient rule for me, I zone in onto that denominator first, and I square it. Whatever's in the denominator, doesn't matter if it's a quantity or in this example, just an integer. And so I'm going to square it, and that jumps in my head first because I'm thinking, okay, whatever's down there happens first in the numerator. And so I just leave it as it is in the numerator. It doesn't get differentiated first. It just happens first. So then that 5 gets copied to the numerator, and then I differentiate the denominator, and those get multiplied. And so I differentiate the numerator, which is at 8x. So, or -8x. Don't lose your signs. So it becomes -8. And so this is just a pattern that with practice we continue to improve. And then I need to do this again because of if you refer back to the rules of the derivative of a quotient, then we need to do that again, but this time we are subtracting. Remember, that's by definition of the derivative of a quotient, and then we're going to differentiate first that 8x, that numerator, that -8x, and it becomes -8, of course, and we're going to differentiate the denominator, and then or we leave the -8x, and then we're going to differentiate the denominator. So that denominator, of course, goes to 0 because that denominator is 5. So the differentiation of 5, or the derivative of 5, would be 0. And so then this is just a pattern that we've practiced and we're familiar with it. And so we just execute. And then now we're left with simplification. And so we look for anything and everything that can simplify. And fortunately, to the far right, all that numerator just simplifies to -40. Sometimes these get really nasty, so we rely heavily on our calculators. Just try not to make any mistakes. Be very, very cautious with that. But otherwise, you just simplify. And so now I'm noticing that -5 can multiply with that -40 over 25 because all these things are are multiplying. So I just multiply those and simplify. And then there's nothing more that I can do. So then I expect that this is the derivative of my original equation. In this example, we have y is equal to the cosecant of a quantity cotangent of x. So then we recognize this because we don't have the cosecant of x. We have the cosecant of the cotangent of x. So we're going to need the chain rule here as well. So I'm thinking, multiplying two things here. What are those things? First of all, I'm going to take the derivative of what it would be if this were the cosecant of x. It would actually be the negative cosecant x times the cotangent of x. That is the derivative of cosecant x. It's just one of those common ones that we find on our cheat sheet, and that is, we see it very often. So at some point we start to memorize it. So the cosecant, or the derivative of the cosecant of x would be negative cosecant x times cotangent x. However, we're not talking about the cosecant of x. We're talking about the cosecant of some quantity. So we need that quantity in there instead of that x. So we're still talking about negative cosecant of something times cotangent of something, but what that something is would be those quantities. So those quantities would be the cotangent of x. So keep that in mind when you're trying to take the derivative of functions such as this one. What is that quantity? And that's what you need. That's what always needs to go inside that parentheses. And then now we need to take the derivative of what's inside that quantity of our original function. And so now we're going to take the derivative of the cotangent of x, which we find on our cheat sheet is the negative cosecant squared of x. And so once we have actually plugged in these values and organized this thing as we should, we can simplify. And so we draw this all out and just pull out what we have and show that it's all multiplying. So we have the negative cosecant cotangent x times the cotangent of the cotangent of x times the negative cosecant squared x. And so we just multiply what we can. And in this case, of course, we can only multiply out those negatives, and we end up with what we have here, which is the derivative of our original function.